Welcome to the AI Academy's Lecture 2 of the Ethical Hacking course. Today we will be covering about the basics of networking and OSI model. The networking refers to the practice of connecting two or more computers and other devices together to share resources and information. This connection can be made via wired or wireless, and it allows for the exchange of data between devices over local or wide areas networks. The networking enables sharing of resources such as files, printers, and internet connections. It also facilitates communication through emails, instant messaging, and video conferencing. It centralizes the data management, making it easier to back up and secure data over network. There are various types of networks. We will discuss about all of them one by one, starting with the LAN. The local area network is a network that connects computers and other devices within a limited geographical area, such as a home, office, or a building. The primary purpose of a LAN is to enable resource sharing and communication among connected devices. LANs can be set up using wired connections, for example, Ethernet cables, or wireless connections over Wi-Fi. The key components of a LAN are computers and devices. These include desktops, laptops, printers, and other network-enabled devices. The switches and routers, where switches connect multiple devices within the LAN, while the routers connect the LAN to external networks, such as the Internet. The cables and wireless access points facilitate the physical or wireless connection between devices. It allows sharing of files, printers, and Internet connections among multiple devices. It enables communication through emails, instant messaging, and video conferencing. Centralizes data management, making it easier to back up and secure data. And allows for the addition of new devices and services without significant restructuring. The next is wide area network. It is a telecommunications network that extends over a large geographic area, which can span cities, countries, or even continents. The primary purpose of a wide area network is to connect multiple smaller networks, such as local area networks or metropolitan area networks, enabling communication and resource sharing across vast distances. The most well-known and largest example of a wide area network is the Internet. The key characteristics of wide area networks are that they have large geographic coverage, unlike LANs, which are limited to a specific location. The wide area networks cover extensive geographical areas, making them suitable for connecting branch offices, data centers, and remote users. The wide area networks can utilize both public networks, like Internet, or the private networks, such as leased lines or VPNs, for connectivity. It can utilize diverse technologies for data transmission, including satellite links, fiber optic cables, and microwave links. And is designed to ensure reliable communication over long distances, often incorporating redundancy to maintain connectivity in case of failures. The wide area network facilitate communication and data exchange between distant locations, supporting global business operations. Organizations can centralize data storage and application management, providing access to users across different locations. It supports various communication methods, including email, video conferencing, and VoIP, enhancing collaboration among remote teams. It can be expanded to include new locations or users as an organization grows. Metropolitan Area Network, also known as MAN, is a type of network that covers a larger geographic area than a local area network but is smaller in scope than a wide area network. MAN typically span a city or a large campus and are used to connect multiple LANs within a metropolitan area. The purpose of a MAN is to provide high-speed connectivity and efficient communication between different locations within the specified area. The MAN covers a larger geographic area, typically a city or a metropolitan region, allowing for connectivity between multiple buildings or locations. MAN provide high-speed network connections, often using fiber optic cables, to ensure fast data transfer and communication between the connected sites. MANs connect multiple LANs, enabling resource sharing, centralized data management, and improved communication across different locations within the metropolitan area. MANs can be owned and operated by government, telecommunications companies, or private enterprises, providing public or private network services. It facilitates efficient communication between various locations within a city, supporting applications like video conferencing, VoIP, and real-time data transfer. The organizations can share resources such as internet connections, servers, and applications across multiple locations, reducing costs and improving efficiency. It allows for centralized management of data and network resources, making it easier to implement security measures and perform data backups. The MANs can be easily expanded to include additional locations or services, supporting the growth of businesses and institutions within the metropolitan area. The Personal Area Network, PAN, is a network that covers a very small area, typically within single room or an individual's immediate surroundings. PANs are used to connect personal devices such as smartphones, tablets, laptops, the wearable devices, and other gadgets for communication and data sharing. The most common technologies used in PANs are Bluetooth and infrared. The PANs have a very short range, usually within 10 meters or 33 feet, making them ideal for personal device connectivity. PANs primarily use wireless technologies like Bluetooth and infrared for establishing connections between devices. It can be set up quickly and easily without the need for complex infrastructure, making them highly flexible and convenient. They are designed to connect a small number of devices for personal use, facilitating data transfer, synchronization, and peripheral sharing. The PANs are simple to set up and use, allowing users to connect their personal devices effortlessly. It enables portable connectivity, allowing users to maintain connections between their devices while on the move. It does not require expensive hardware or infrastructure, making them a cost-effective solution for personal networking needs. The PANs facilitate quick data transfer and synchronization between devices, enhancing productivity and convenience for users. Next, we will discuss about VPN. The Virtual Private Network is a technology that extends a private network across a public network, such as the Internet, allowing users to send and receive data securely as if their devices were directly connected to the private network. VPNs create a secure, encrypted tunnel between the user's device and the VPN server, protecting data from interception and ensuring privacy. It uses strong encryption protocols to secure data transmitted over the public network, making it unreadable to unauthorized parties. It enables remote users to access resources on a private network from anywhere in the world, providing flexibility and convenience. It can mask the user's IP address, enhancing online privacy and preventing tracking by websites and third parties. The VPNs allow users to access content and services that may be restricted based on geographic location by routing traffic through servers in different regions. The VPNs ensure that sensitive data, such as financial transactions and personal information, is transmitted securely over the Internet. By encrypting data and masking IP addresses, VPNs protect users' online privacy and prevent tracking and surveillance. VPNs facilitate remote work by allowing employees to securely access company resources and data from anywhere. It enables users to bypass censorship and geo-restrictions, allowing access to a broader range of online content and services. Let us now discuss about OSI Model. The OSI Open Systems Interconnection Model is a conceptual framework used to understand and standardize the functions of a telecommunication or computing system without regard to its underlying internal structure and technology. The OSI model divides the functions of a network into 7 distinct layers, each with specific responsibilities. The OSI model provides a universal set of standards for networking technologies, ensuring interoperability between different systems and devices. It simplifies the process of troubleshooting network issues by isolating problems to specific layers, and helps in the design and development of network protocols and technologies by providing a clear framework. The OSI model has 7 layers, and each layer has different roles to play. Let us start with the physical layer, also known as Layer 1. It is the first and lowest layer in the OSI model. Its primary function is to transmit raw bit streams over a physical medium, ensuring that data sent from one device is received by another without errors. This layer deals with the physical connection between devices and the transmission and reception of data in the form of electrical signals, light pulses, or radio waves. The physical layer is responsible for converting digital data from the data link layer into signals that can be transmitted over the network medium. These signals can be electrical, optical, or radio waves. This layer defines the hardware standards for network devices, including cables, connectors, and network interface cards, NICs. And it also handles the physical aspects of network connections, such as voltage levels, timing of signals, and the physical layout of the network. The components of the physical layer are the cables for data transmission, including twisted pair cables, Ethernet, coaxial cables, and fiber optic cables. The switches and hubs connect multiple network devices and manage data traffic at the physical level. And the network interface cards, NICs, it is hardware components installed in devices to enable network connections, converting digital data into physical signals and vice versa. The physical layer protocols are Ethernet, a widely used LAN technology that defines wiring and signaling standards for the physical layer. USB, Universal Serial Bus, is a standard for connecting peripherals to computers, allowing data transmission and power supply. And Bluetooth, a wireless technology standard for exchanging data over short distances using radio waves. For example, the electrical signals, used in wired connections like Ethernet and USB, where data is transmitted as electrical impulses through cables. And the radio waves, used in wireless technologies like Wi-Fi and Bluetooth, where data is transmitted through the air using radio frequencies. Next is data link layer or layer 2. The data link layer is the second layer in the OSI model. Its primary function is to provide reliable, error-free transfer of data frames between nodes over the physical layer. This layer ensures that data is properly packaged into frames and transmitted to the correct destination, while also handling error detection and correction. The key functions of the data link layer are error detection and correction. The data link layer detects and corrects errors that may occur during data transmission over the physical layer. This ensures that data is transferred accurately between devices. The frame synchronization. This layer organizes data into frames, which are manageable units for transmission. Each frame contains the necessary synchronization information to ensure proper data alignment and interpretation. Flow control manages the rate of data transmission between devices to prevent congestion and ensure smooth communication. And it uses hardware addresses, MAC addresses, to identify and route data frames to the correct destination within a local network. The components of the data link layer are switches. They operate at the data link layer, using MAC addresses to forward data frames to the appropriate destination within a local network. And the bridges, that connect multiple network segments, filtering and forwarding data frames based on MAC addresses to reduce traffic and improve a network efficiency. The Layer 2 protocols are Ethernet. It is a widely used LAN technology that defines the format and transmission rules for data frames at the data link layer. The PPP, point-to-point protocol, is used for direct communication between two network nodes, providing encapsulation, authentication, and error detection. And the ARP, Address Resolution Protocol, is used to map IP addresses to MAC addresses, allowing devices to locate each other on a local network. For example, a unique hardware addresses are assigned to network interfaces, used to identify devices on a local network. And the units of data that include a header, with addressing and control information, and a payload, the actual data being transmitted, are called frames. Next layer is the network layer, Layer 3. The network layer is the third layer in the OSI model. Its primary function is to determine how data is sent to the receiving devices across multiple networks. This layer handles logical addressing and routing, ensuring that data packets reach their correct destination efficiently. The key functions of the network layer are the logical addressing. The network layer assigns and uses logical addresses, such as IP addresses, to uniquely identify devices on a network. This allows for proper identification and communication between devices. Routing layer is responsible for determining the best path for data packets to travel across interconnected networks. Routers and Layer 3 switches analyze the network topology and make routing decisions to forward packets to their destination. And the packet forwarding, the network layer breaks down data into packets, which are then forwarded to the next network node along the determined path. Each packet may take a different route to reach the destination. The key components of the Layer 3 are: routers operates at the network layer, analyzing IP addresses and making routing decisions to forward packets between networks. And the advanced network switches that perform routing functions in addition to traditional switching, using IP addresses to forward packets within a local network or between networks. The main Layer 3 protocols are the IP, Internet Protocol, the primary protocol used at the network layer, responsible for addressing, routing, and fragmenting data packets for transmission across networks. ICMP, Internet Control Message Protocol, a protocol used for error reporting and diagnostics, allowing network devices to send messages about network conditions. And the IGMP, Internet Group Management Protocol used to manage multicast group memberships, allowing devices to communicate with multiple hosts simultaneously. For example, the IP addresses are the logical addresses assigned to network devices, used to identify and locate devices on a network. And the packets are the units of data that include a header with addressing and control information and a payload, which is the actual data being transmitted. Let us now discuss about the transport layer, Layer 4. The transport layer is the fourth layer in the OSI model. Its primary function is to ensure complete data transfer and error recovery, providing reliable, end-to-end communication between devices across a network. The transport layer handles the segmentation and reassembly of data, flow control, and error detection and correction. The key functions of the transport layer are: the transport layer provides end-to-end communication control, ensuring that data is delivered accurately and in the correct sequence from the source to the destination. This layer breaks down large data streams into smaller segments for easier transmission and then reassembles them at the destination. It also manages the rate of data transmission between devices to prevent congestion and ensure efficient communication. And the transport layer detects errors in transmitted data and implements mechanisms to recover lost or corrupted data. The key components of the transport layer are: gateways. It connects to different networks and operate at various layers of the OSI model, including the transport layer, to manage data flow and ensure proper routing and delivery. The firewalls, a security device that monitor and control incoming and outgoing network traffic based on predetermined security rules. They can operate at the transport layer to filter traffic based on port numbers and protocols. And the transport layer protocols are: TCP, Transmission Control Protocol, a connection-oriented protocol that provides reliable data transfer with error detection, retransmission, and flow control. It ensures that data is delivered in the correct order and without duplication. And the UDP, User Datagram Protocol, which is a connectionless protocol that provides fast, but unreliable, data transfer. It does not guarantee delivery, order, or error correction, making it suitable for applications where speed is more critical than reliability, such as streaming. The examples are the segments, which are the units of data used by TCP, including the header, with control information, and a payload, the actual data being transmitted. And the datagrams, the units of data used by UDP, like segments, but without the reliability features of TCP. Let us now discuss about session layer, Layer 5. The session layer is the fifth layer in the OSI model. Its primary function is to manage sessions between applications. This layer establishes, manages, and terminates connections between applications on different devices, ensuring that data is properly synchronized and organized. The key functions are that the session layer initiates and establishes a connection between two applications on different devices, enabling them to communicate. Once a session is established, this layer manages the data exchange, maintaining synchronization and ensuring that the session remains active. And the session layer terminates the session once the communication is complete, releasing the resources allocated for the session. The component is the gateways which connect different networks and can operate at multiple layers of the OSI model, including the session layer, to manage and facilitate session establishment and termination. The session layer protocols are NetBIOS, Network Basic Input/Output System, protocol that provides services related to the session layer, allowing applications on different computers to communicate within a local network. The RPC, Remote Procedure Call, protocol allows a program to execute a procedure on a remote server as if it were local, facilitating communication between distributed applications. The PPTP protocol used to create virtual private networks, VPNs, establishing a secure session for data transmission over public networks. For example, initiating a connection between a client application and a server application to start communication. Keeping the session active and synchronized, ensuring that data is exchanged correctly and in the right order. And closing the connection and releasing resources after the communication session has ended. Let us now move on to the presentation layer, layer 6. The presentation layer is the sixth layer in the OSI model. Its primary function is to translate data between the application layer and the network, ensuring that data is in a usable format for the receiving application. This layer is also responsible for data encryption and decryption, data compression, and data translation. The key functions are data translation. The presentation layer translates data from the format used by the application layer into a common format for transmission and vice versa. This ensures that data is correctly interpreted by different systems. This layer provides data security by encrypting data before it is transmitted and decrypting data upon arrival, ensuring that sensitive information is protected during transit. And the presentation layer compresses data to reduce the amount of data that needs to be transmitted, improving the efficiency of data transfer. The components are gateways that connect different networks and can operate at multiple layers of the OSI model, including the presentation layer, to manage data translation and conversion. The presentation layer protocols are SSL/TLS, Secure Sockets Layer/Transport Layer Security. These protocols provide secure communication over a computer network by encrypting data and ensuring data integrity. JPEG, Joint Photographic Experts Group, is a standard for compressing image files, ensuring that images are transmitted in a format that can be displayed correctly by different systems. And the MPEG, Moving Picture Experts Group, a standard for compressing video and audio files, enabling efficient transmission and playback of multimedia content. For example, the data encryption, encrypting sensitive information such as passwords or credit card numbers before sending them over the network. Reducing the size of large files, such as images or videos, to speed up transmission and save bandwidth. Converting data from one character encoding to another, such as from ASCII to EBCDIC, to ensure compatibility between different systems. And finally, the application layer, layer 7. The application layer is the seventh and topmost layer in the OSI model. This layer provides network services directly to user applications and is the layer with which the user interacts. It is responsible for facilitating communication between software applications and the network, ensuring that the data is properly presented and utilized. The key functions are the network services to applications. The application layer offers various network services to user applications, enabling them to communicate over the network. This layer is where users interact with the network through software applications like web browsers, email clients, and file transfer programs. It ensures that data is presented in a readable format for the application and that it is correctly delivered to the appropriate service. The components of the layer 7 are application software, programs that run on the application layer, providing services such as web browsing, email communication, file transfers, and more. And the protocols are HTTP, Hypertext Transfer Protocol, a protocol used for transmitting hypertext, web pages, over the Internet, enabling web browsing. FTP, File Transfer Protocol, is a protocol for transferring files between computers over a network, allowing users to upload and download files. SMTP, Simple Mail Transfer Protocol, a protocol used for sending emails across networks, ensuring the proper delivery of email messages. The DNS, Domain Name System, a protocol that translates human-readable domain names into IP addresses, enabling users to access websites using easy-to-remember names. For example, web browsers applications like Google Chrome, Mozilla Firefox, and Microsoft Edge that use HTTP to access and display web pages. Email clients programs like Microsoft Outlook, Gmail, and Apple Mail that use SMTP to send emails and IMAP/POP3 to receive emails. The file transfer programs, software like FileZilla and WinSCP that use FTP to transfer files between local and remote computers. Let us now look into the interlayer interaction in the OSI model. The OSI model is a conceptual framework used to understand and implement standard protocols in network communications. Each layer in the OSI model interacts directly with the layer above and below it. This interaction ensures that each layer only needs to focus on its specific function while relying on the adjacent layers for support. This design provides modularity, allowing different layers to be developed and updated independently. The encapsulation and decapsulation are the fundamental process in the OSI model that ensure data is properly packaged and interpreted as it moves across the network. The encapsulation is executed as data moves down the OSI layers from the application layer to the physical layer. Each layer adds its own header and sometimes trailer information to the data. This added information is necessary for the corresponding layer on the receiving end to process the data correctly. At the application layer, the data originates as user inputs in an application, such as an email message or a file transfer request. The presentation layer may add formatting information or encrypt the data to ensure that it can be correctly interpreted or kept secure during transmission. In the session layer, a session header might be added here to manage the session and ensure that the entire communication can be reassembled and synchronized at the receiving end. At the transport layer, the data is divided into smaller segments, and a transport header, which includes sequence numbers and error-checking information, is added. In the network layer, the transport segments are encapsulated into packets with network headers containing source and destination IP addresses and routing information. At data link layer, each packet is encapsulated into frames with data link headers and trailers, including MAC addresses for the source and destination devices. And finally, the frames are converted into electrical signals, light pulses, or radio waves for transmission over the physical medium at the physical layer. The encapsulation process ensures that data is systematically prepared for transmission, with each layer adding the necessary information to handle its specific role. Let us now talk about decapsulation. The decapsulation is executed as data moves up the OSI layers from the physical layer to the application layer. Each layer removes its corresponding header and processes the remaining information. At the physical layer, the raw signals are received and converted back into data frames. At the data link layer, the data link layer removes the data link header and trailer, processes the frames, and passes the resulting packets to the network layer. In the network layer removes the network header, processes the packets, and forwards the resulting segments to the transport layer. The transport layer reassembles the segments into complete messages or data streams, removing the transport header, and passes the data to the session layer. The session layer synchronizes and reassembles the data streams, removing the session header, and forwards the data to the presentation layer. The presentation layer decrypts or formats the data as needed, removing the presentation header, and passes the data to the application layer. And finally, the data reaches the application layer, where it is interpreted and presented to the user in a readable format. The decapsulation process ensures that data is correctly interpreted and utilized at the receiving end, with each layer removing the added information and processing the remaining data accordingly. Of sending an email using an email client to illustrate how the OSI model functions. In the application layer, a user composes an email using an email client, like Microsoft Outlook or Gmail. When the user hits Send, the email client uses the Simple Mail Transfer Protocol, SMTP, to format the email and initiate the sending process. At the presentation layer, the email content might be formatted in ASCII or Unicode, and it could be encrypted using SSL/TLS to ensure privacy during transmission. This ensures that the data can be correctly interpreted by the recipient's email client and remains secure. In the session layer, the email client establishes a session with the recipient's mail server. This session ensures that the email is sent in a continuous stream, managing the dialogue between the sender's and recipient's systems. At the transport layer, the email data is segmented into smaller chunks, and each segment is assigned a sequence number. The transmission control protocol ensures that each segment is delivered reliably, in the correct order, and without errors. If any segment is lost, TCP will retransmit it. At the network layer, the segments are encapsulated into IP packets, with each packet containing the sender's and recipient's IP addresses. The Internet Protocol, IP, determines the best route for the packets to travel across the network to reach the recipient's mail server. At the data link layer, the IP packets are encapsulated into frames with MAC addresses of the sender's and recipient's devices. These frames are prepared for transmission over the local network, whether it's an Ethernet LAN or a Wi-Fi network. And finally, the frames are converted into electrical signals, light pulses, or radio waves, depending on the transmission medium. These signals travel over the physical medium like copper wires, fiber optics, or air to the recipient's network at the physical layer. As the email data travels through each layer, it is encapsulated with the necessary headers and trailers to ensure proper handling and delivery. When the recipient's mail server receives the data, the process is reversed. At physical layer, the server receives the electrical signals, light pulses, or radio waves and converts them back into data frames. At data link layer, the server removes the data link header and trailer, processes the frames, and passes the packets to the network layer. At network layer, the server removes the network header, processes the packets, and forwards the segments to the transport layer. At transport layer, the server reassembles the segments into the complete email message, removing the transport header, and passes the data to the session layer. At session layer, the server manages the session, ensuring the data stream is synchronized and reassembled correctly, and forwards the data to the presentation layer. At the presentation layer, the server decrypts and formats the email data as needed, removing the presentation header, and passes the data to the application layer. And finally, at the application layer, the email server software processes the email and delivers it to the recipient's inbox, where it can be accessed by the recipient's email client. This example illustrates how each layer in the OSI model contributes to the seamless transmission and reception of data, ensuring that the email is sent and received correctly, securely, and efficiently. The OSI model provides a structured approach to understanding and implementing network communication. Each layer has a specific role and interacts with the layers above and below it to ensure reliable data transfer. Encapsulation and decapsulation are essential processes that enable data to be correctly packaged and interpreted as it moves across the network. By dividing the communication process into distinct layers, the OSI model allows for modular development and troubleshooting. This modularity ensures that changes or improvements can be made to individual layers without affecting the entire system, making network design, implementation, and maintenance more manageable. Understanding the OSI model and the role of each layer is fundamental for anyone involved in network administration, development, or security. It provides a clear framework for how data is transmitted and received, highlighting the importance of each layer in ensuring effective and secure communication. The OSI model is essential for understanding how data is transmitted and received over a network, providing a clear framework for network communication and troubleshooting. Next, we will look into the basics of networking devices and protocols. Router. The router is a networking device that routes data packets between different networks, effectively directing traffic on the Internet. It connects multiple networks, such as a local area network and a wide area network, and directs data packets to their destination by choosing the best path. Routers are essential for ensuring efficient data flow across interconnected networks and the broader Internet. The main components of the router are: internal processor is also the router's brain, responsible for executing instructions and managing data flow. It processes incoming and outgoing data packets, determining the best route for each packet based on its destination address. For example, the home broadband routers are commonly used in households to connect multiple devices, such as computers, smartphones, and smart TVs, to the Internet. These routers often include integrated wireless access points, Wi-Fi, and Ethernet ports for wired connections. The enterprise routers are high-performance routers used by businesses to manage large volumes of data traffic across complex networks. They offer advanced features like quality of service, QoS, virtual private network, VPN, support, and multiple WAN interfaces. And the virtual routers are software-based routers that run on virtual machines or cloud environments. They provide routing capabilities without the need for dedicated hardware, offering flexibility and scalability for modern network infrastructures. Routers play a crucial role in modern networking by managing data traffic between different networks and ensuring efficient and secure data transmission. Here's a closer look at how routers perform their functions. Routing data packets. Routers receive data packets from connected devices and determine the best path to forward these packets to their destination. This process involves examining the destination IP address of each packet and consulting the routing table to find the optimal route. The routing table contains information about various network paths, including metrics like hop count, latency, and bandwidth. Routers use routing algorithms such as distance vector or link state to calculate the best path based on these metrics. Routers connect multiple networks, such as a home LAN, to the Internet or different segments of an enterprise network. They act as intermediaries, enabling devices on different networks to communicate with each other. By segmenting networks, routers enhance security and performance. For example, in an enterprise environment, routers can separate internal traffic from external traffic and protect sensitive data, and improving network efficiency. Directing traffic. Routers use routing protocols, such as OSPF, BGP, or RIP, to exchange information with other routers and update their routing tables dynamically. These protocols help routers learn about network changes and adapt their routing decisions accordingly. Routing protocols ensure that routers can handle dynamic network environments, where network paths may change due to congestion, hardware failures, or other factors. Understanding the components of routers helps explain how they perform their functions effectively. The internal processor, often referred to as the central processing unit, CPU, of the router, executes the instructions provided by the firmware. It processes incoming data packets, performs routing calculations, and manages data traffic. High-performance routers may feature multi-core processors to handle large volumes of data and complex routing tasks, ensuring smooth and efficient operation. The firmware is the software that runs on the router, providing the necessary instructions for its operation. It includes the operating system, routing protocols, security features, and management interfaces. Firmware updates are essential for maintaining router performance and security. Manufacturers releases updates to fix bugs, enhance features, and patch security vulnerabilities. Routing tables are databases that store information about network paths. They include details like destination IP addresses, next hop addresses, and metrics used to determine the best path for data packets. The routers continuously update their routing tables based on information received from routing protocols and network traffic analysis. This dynamic updating ensures that routers can adapt to changes in network topology and maintain efficient data routing. The examples of routers are home broadband routers. The home routers are designed for residential use, providing internet connectivity to multiple devices within a household. They often include built-in Wi-Fi access points, enabling wireless connections for smartphones, tablets, and laptops. These routers typically feature user-friendly interfaces for easy configuration and management. Users can set up network settings, create guest networks, and implement parental controls to manage internet access. The enterprise routers are designed for business environments, where high performance, reliability, and advanced features are required. They support large volumes of data traffic and offer robust security features to protect sensitive business information. Enterprise routers may include multiple internet interfaces for redundancy and load balancing, ensuring uninterrupted connectivity. They also support advanced features like VPNs for secure remote access and QoS for prioritizing critical applications. The virtual routers are software-based solutions that run on virtual machines or cloud environments. They provide routing capabilities without the need for dedicated hardware, offering flexibility and scalability. Virtual routers are ideal for modern network infrastructures, where organizations may use cloud services and virtualized environments. They can be easily deployed and managed, allowing businesses to scale their network resources as needed. In summary, the routers are essential networking devices that manage data traffic between different networks, ensuring efficient and secure communication. By connecting multiple networks and directing data packets to their destination, routers play a critical role in the functioning of the Internet and modern network infrastructures. Understanding the components and functionality of routers helps explain how they perform their tasks effectively. The internal processor, firmware, and routing tables work together to process data packets, determine the best paths, and manage data traffic dynamically. Different types of routers, including home broadband routers, enterprise routers, and virtual routers, cater to various networking needs, from residential internet connectivity to complex enterprise networks and the cloud-based environments. By providing reliable data routing and connectivity, routers enable seamless communication across networks, supporting the diverse and dynamic nature of modern digital communication. Next, we will be looking into the switch. The switch is a networking device that connects devices within a single network, such as a local area network or also called as LAN. It uses MAC or Media Access Control addresses to forward data to the correct device, ensuring efficient and accurate data delivery. Switches operate at the data link layer or layer 2 of the OSI model, although some advanced switches can also operate at higher layers such as layer 3. The switches play a crucial role in modern networking by connecting multiple devices within a single network and ensuring efficient data transmission. Here's a closer look at how switches perform their functions. The switches connect various devices within a LAN, allowing them to communicate with each other. Each device is connected to the switch through a physical port. When a device sends data, the switch receives the data frame through the corresponding port and uses the MAC address table to determine the destination port. The switch then forwards the data frame to the correct port, ensuring that it reaches the intended device. The MAC address table is a critical component of a switch. It maps each device's MAC address to the specific port it is connected to. This table is dynamically updated as devices connect and disconnect from the network. When a data frame arrives, the switch examines the destination MAC address, consults the MAC address table, and forwards the frame to the appropriate port. Next is switching fabric. The switching fabric is the internal architecture of the switch that manages data paths between ports. It enables the high-speed transfer of data frames within the switch, ensuring minimal latency and optimal performance. The advanced switches may feature a non-blocking switching fabric, allowing multiple data transfers to occur simultaneously without interference, further enhancing network efficiency. Let us now look into the components of switches. Understanding the components of switches helps explain how they perform their functions effectively. The ports. The switches come with multiple ports to connect various network devices. Each port typically corresponds to an Ethernet interface, allowing wired connections using Ethernet cables, or it can be a fiber port also. And the ports can vary in speed, supporting different Ethernet standards such as Fast Ethernet, 100 megabits per second, Gigabit Ethernet, and 10 gigabit Ethernet, depending on the switch model. The MAC address table is maintained by the switch's internal processor. It dynamically learns and stores the MAC addresses of devices connected to its ports. When a new device connects to the switch, its MAC address is added to the table, along with the corresponding port number. The table is continuously updated as devices connect, disconnect, or move within the network. The switching fabric is the backbone of the switch, responsible for the internal data transfer between ports. It ensures that data frames are quickly and efficiently routed from the source port to the destination port. The performance of the switching fabric determines the switch's overall throughput and capacity to handle multiple data transfers simultaneously. Let us now look into the examples of switches. The managed switches offer advanced network management features, making them suitable for complex network environments. They provide administrators with control over network traffic, security settings, and configuration options. Features like VLANs allow administrators to segment the network into separate virtual networks, enhancing security and performance. QoS settings enable prioritization of critical applications and services, ensuring optimal performance for important network traffic. The managed switches can be configured and monitored through a web interface, command line interface, or dedicated network management software. The unmanaged switches are simple, plug-and-play devices that require no configuration. They are ideal for small or home networks where advanced features are not needed. These switches automatically manage data forwarding based on MAC addresses and do not offer any customization or management options. They provide a cost-effective solution for basic network connectivity. The PoE, Power over Ethernet, switches provide both data connectivity and electrical power to connected devices over the same Ethernet cable. This feature simplifies the installation of network devices by eliminating the need for separate power supplies. PoE switches are commonly used to power devices like IP cameras, wireless access points, VoIP phones, and other network devices that require power. They support different PoE standards, such as IEEE 802.3AF, PoE, and IEEE 802.3AT, PoE+, which define the amount of power that can be delivered. To summarize, switches are essential networking devices that connect multiple devices within a single network, ensuring efficient and accurate data transmission. By using MAC addresses to forward data frames to the correct device, switches play a critical role in the functioning of local area networks. Understanding the components and functionality of switches helps explain how they perform their tasks effectively. Ports, the MAC address table, and the switching fabric work together to manage data transfer, maintain network efficiency, and ensure reliable connectivity. Different types of switches, including managed switches, unmanaged switches, and PoE switches, cater to various networking needs, from simple home networks to complex enterprise environments. Managed switches offer advanced features and control, the unmanaged switches provide basic connectivity, and PoE switches deliver power and data over a single cable, simplifying device installation. By providing reliable and efficient data transfer within a network, switches enable seamless communication between connected devices, supporting the diverse and dynamic nature of modern digital communication. Let us now look into the hub. A hub is a basic networking device that connects multiple Ethernet devices, making them act as a single network segment. It operates at the physical layer, layer 1, of the OSI model. When a data packet arrives at one of its ports, the hub broadcasts the packet to all other ports, regardless of the destination address. This broadcasting method allows all connected devices to see the packet, but only the intended recipient processes the data. The functionality of hubs are that the hubs play a fundamental role in early network designs by providing a central connection point for Ethernet devices within a local area network. Here's a closer look at how hubs perform their functions. Hubs connect multiple Ethernet devices, allowing them to communicate within the same network segment. Each device connects to the hub through an Ethernet port. When a device sends data, the hub receives the data packet through the corresponding port and broadcasts it to all other ports. This means all connected devices receive the packet, but only the intended recipient processes the data. Hubs operate on a principle of broadcasting incoming data packets to all connected devices. This method ensures that the data reaches its destination but can lead to inefficiencies. Since hubs do not filter or direct packets based on the destination address, they create a lot of unnecessary network traffic. All devices receive all packets, which can lead to collisions and network congestion. All devices connected to a hub share the same collision domain. A collision domain is a network segment where data packets can collide with one another if multiple devices try to send data simultaneously. When a collision occurs, the involved devices must wait for a random period before attempting to retransmit the data. This process, known as collision detection and backoff, can reduce network performance as the number of collisions increases with more devices and increasing waiting time. Understanding the components of hubs helps explain how they perform their functions effectively. The multiple ports. The hubs come with multiple Ethernet ports to connect various devices within a network segment. Each port typically corresponds to an Ethernet interface, allowing wired connections using Ethernet cables. The number of ports on a hub can vary, with common configurations including 4, 8, 12, or 24 ports. The collision domain. The collision domain is a key characteristic of hubs. It encompasses all devices connected to the hub, meaning that any data transmission by one device can potentially collide with transmissions from other devices within the same domain. This shared collision domain is a major limitation of hubs, as it can lead to frequent collisions and reduced network efficiency, especially in networks with high traffic. Let us now discuss about the examples of hubs such as the passive hub. A passive hub is a simple device that provides basic connectivity without any amplification or signal regeneration. It merely serves as a conduit for data signals, allowing them to pass through from one device to another. Passive hubs do not require a power source, as they do not perform any processing or amplification of signals. They are typically used in small, simple networks where signal degradation is not a concern. An active hub amplifies or regenerates incoming signals before broadcasting them to other ports. This helps maintain signal strength over longer distances, ensuring that data signals remain strong and clear. The active hubs require a power source to perform signal amplification and regeneration. They are suitable for larger networks or environments where signal degradation could be an issue. An intelligent hub offers additional features such as network management and monitoring capabilities. It can provide basic diagnostics, allowing network administrators to monitor network performance and detect issues. Intelligent hubs may include features like port status indicators, error detection, and remote management capabilities. These features can help improve network reliability and make troubleshooting easier. The hubs are basic networking devices that connect multiple Ethernet devices within a single network segment, enabling communication between connected devices. By broadcasting incoming data packets to all ports, hubs ensure that data reaches its destination, although this method can lead to inefficiencies and collisions. Understanding the components and functionality of hubs helps explain how they perform their tasks effectively. Multiple ports provide connectivity for various devices, while the collision domain characterizes the network segment where data collisions can occur. While hubs have largely been replaced by more advanced devices like switches and routers in modern networks, they played a crucial role in the development of early Ethernet networks. By providing a simple and effective way to connect multiple devices, hubs contributed to the growth and expansion of local area networks. Next, we will discuss about the modem. A modem is a device that modulates and demodulates signals for data transmission over telephone lines, cable, or fiber optics. Its primary function is to convert digital data from a computer or network into analog signals for transmission over these media and vice versa. This conversion process allows data to be transmitted over long distances using existing telephone, cable, or fiber infrastructure. Modems play a critical role in enabling internet connectivity by converting data between different formats suitable for transmission and reception. Here's a closer look at how modems perform their functions. When data is sent from a computer or network to the internet, the modem modulates the digital data into analog signals. This process involves encoding the digital information onto a carrier signal that can be transmitted over telephone lines, coaxial cables, or fiber optic cables. Demodulation is performed when data is received from the internet. The modem demodulates the incoming analog signals back into digital data. This process involves decoding the carrier signal to extract the digital information that can be processed by the computer or network. For the data transmission, the modems enable data transmission over long distances using existing telephone, cable, or fiber infrastructure. By converting digital data into analogy signals and vice versa, modems make it possible to use these infrastructures for internet connectivity. This conversion process allows for efficient use of the available bandwidth and ensures that data can be transmitted reliably over different types of media. Interface connectors. The modems have interface connectors for connecting to the ISP infrastructure and the local network. These connectors vary depending on the type of modem and the medium used for data transmission. Common connectors include phone jacks for DSL modems, coaxial cable ports for cable modems, and fiber optic ports for fiber modems. Ethernet ports are also included for connecting the modem to a router or directly to a computer. Let us now look into the components of modems. The modulator is responsible for converting digital data into analog signals. This component takes the binary data from the computer or network and encodes it onto a carrier signal suitable for transmission over telephone lines, coaxial cables, or fiber optics. The modulation process involves techniques such as amplitude modulation, AM, frequency modulation, FM, or phase modulation, PM, depending on the type of modem and the transmission medium. The demodulator is responsible for converting incoming analog signals back into digital data. This component decodes the carrier signal to extract the binary data that can be processed by the computer or network. The demodulation process involves reversing the modulation technique used during transmission, ensuring that the original digital data is accurately recovered. The modems have various interface connectors for connecting to the ISP infrastructure and the local network. These connectors provide the physical interface for data transmission and reception. The common connectors include RJ11 phone jacks for DSL modems, F-type coaxial connectors for cable modems, and SC or LC fiber connectors for fiber modems. Ethernet ports called as RJ45 are also included for connecting the modem to a router or computer. The examples of modems are like DSL. They are used for digital subscriber line internet connections. They transmit data over traditional telephone lines, allowing simultaneous use of the internet and phone line. DSL modems typically include an integrated splitter that separates the data signal from the voice signal, ensuring that both services can operate concurrently without interference. Cable modems. The cable modems are used for broadband internet connections provided by cable television companies. They use the same coaxial cables that deliver cable TV service to transmit data. Cable modems are often integrated with a router to provide both wired and wireless connectivity within a home or office network. The fiber modems, they are used for fiber optic internet connections. They convert light signals transmitted over fiber optic cables into digital data for computers and networks. Fiber modems are often part of an optical network terminal, ONT, in fiber to the home, FTTH, installations. The ONT serves as the interface between the fiber optic network and the local network, providing high-speed internet connectivity. The modems are essential networking devices that enable internet connectivity by modulating and demodulating signals for data transmission over telephone lines, cable, or fiber optics. By converting digital data into analog signals and vice versa, modems facilitate efficient data transmission over long distances using existing infrastructure. Understanding the components and functionality of modems helps explain how they perform their tasks effectively. The modulator and demodulator work together to ensure accurate data conversion, while interface connectors provide the necessary physical connections for data transmission. Let us now look into the Network Interface Card, also known as NIC. A network interface card provides a physical connection to a network for a computer or other device. It acts as an interface between the device and the network, converting data from the device into electrical signals or radio signals for wireless NICs for transmission over the network. Similarly, it receives incoming network signals and converts them back into data for the device. NICs are essential for enabling network communication in both wired and wireless networks. They provide the necessary hardware interface for devices to connect to and communicate over a network. Here's a closer look at how NICs perform their functions. Providing network connectivity, NICs allow devices to connect to a network, whether it's a local area network or a broader network such as the Internet. They serve as the bridge between the device's internal bus, such as PCI or PCIe, and the network medium, such as Ethernet, Wi-Fi, or fiber optic. By converting data into the appropriate signal type for transmission over the network and vice versa, NICs enable devices to send and receive data over the network. Handling data transmission. When a device needs to send data over the network, the NIC takes the digital data from the device's CPU and converts it into electrical signals, for wired NICs, or radio signals, for wireless NICs. These signals are then transmitted over the network medium to the destination device. Upon receiving data from the network, the NIC converts the incoming signals back into digital data and passes it to the device's CPU for processing. Ensuring unique identification with MAC address. Each NIC has a unique MAC address, which is used to identify the device on the local network. The MAC address is a 48-bit identifier that ensures that data packets are delivered to the correct device. The NIC uses the MAC address to filter and process incoming data, ensuring that only data intended for that device is accepted and processed. Let us now discuss about components of network interface cards. MAC address. The MAC address is a unique identifier assigned to each NIC. It is embedded in the NIC's hardware and is used for communication at the data link layer. The MAC address consists of 6 pairs of hexadecimal digits and is used to ensure that data packets are correctly addressed and routed to the appropriate device on the local network. The transceiver is the component responsible for transmitting and receiving network signals. In wired NICs, it converts digital data into electrical signals for transmission over Ethernet cables and vice versa. In wireless NICs, the transceiver handles radio frequency signals, converting digital data into radio waves for wireless transmission and vice versa. The interface connectors. NICs have various interface connectors to link them to the network medium. For Ethernet NICs, this is typically an RJ45 port for connecting Ethernet cables. Wireless NICs have built-in antennas for Wi-Fi communication. Fiber optic NICs have specialized connectors, such as SC or LC connectors, for connecting to fiber optic cables. Examples of network interface cards are Ethernet NICs. Ethernet NICs are used for wired network connections via Ethernet cables. They are the most common type of NIC and are found in a wide range of devices, including desktops, laptops, and servers. The Ethernet NICs support various Ethernet standards, such as Fast Ethernet, Gigabit Ethernet, and 10 Gigabit Ethernet, providing flexible options for network speed and performance. The wireless NICs, it enable devices to connect to wireless networks using Wi-Fi. These NICs have built-in antennas and support various Wi-Fi standards, such as 802.11n, 802.11ac, and 802.11 AX, for different levels of speed and coverage. The wireless NICs are commonly used in portable devices like laptops, smartphones, tablets, and IoT devices, providing the convenience of wireless connectivity. The fiber optic NICs are designed for high-speed network connections over fiber optic cables. They provide the necessary hardware interface for transmitting and receiving data over long distances with minimal signal loss. The fiber optic NICs are used in environments requiring high bandwidth and long-distance communication, such as data centers, enterprise networks, and telecommunication systems. They support various fiber optic standards and connectors, providing options for different network architectures and requirements. NICs are essential components for enabling network connectivity in both wired and wireless networks. By providing a physical connection to the network and converting data into appropriate signals for transmission, NICs facilitate communication between devices and the network. Understanding the components and functionality of NICs helps explain how they perform their tasks effectively. The MAC address ensures unique identification, the transceiver handles data transmission and reception, and the interface connectors link the NIC to the network medium. Different types of NICs, including Ethernet NICs, wireless NICs, and fiber optic NICs, cater to various networking needs. Ethernet NICs provide wired connectivity, wireless NICs enable Wi-Fi connections, and fiber optic NICs offer high-speed connections over long distances. By enabling reliable and efficient network communication, NICs play a critical role in the functioning of modern digital networks, supporting the diverse and dynamic nature of network devices and applications. Next, we will look into the access point. An access point is a networking device that allows wireless devices to connect to a wired network using Wi-Fi. It extends the wireless coverage of an existing network, enabling devices such as laptops, smartphones, tablets, and IoT devices to connect wirelessly to the network. The access points are essential for providing wireless access in areas where a wired connection is impractical or impossible. Access points play a crucial role in extending network connectivity by providing a bridge between wired and wireless networks. Here's a closer look at how access points perform their functions. The access points allow various wireless devices to connect to the network. Devices like laptops, smartphones, tablets, and IoT devices communicate with the APs using Wi-Fi. The APs receives data from these devices, converts it into a format suitable for wired transmission, and forwards it to the wired network. APs extend the wireless coverage of an existing network. By placing multiple access points strategically, a network can cover larger areas, such as entire buildings, campuses, or public spaces. This extended coverage ensures that users can maintain a reliable wireless connection as they move throughout the coverage area. Access points serve as bridges between wired and wireless segments of a network. They connect to the wired network via an Ethernet port, allowing wireless devices to access network resources, such as servers, printers, and the Internet. This bridging capability is essential for integrating wireless devices into the broader network infrastructure. The components of access points are radio transceiver. It is responsible for transmitting and receiving radio signals. It converts digital data from the wired network into radio waves for wireless transmission and converts incoming radio waves back into digital data. The transceiver operates on specific frequency bands, such as 2.4 GHz and 5 GHz, and uses various Wi-Fi standards, such as 802.11n, 802.11ac, or 802.11 AX, to communicate with wireless devices. The antennas enhance the range and quality of the wireless signal. They can be internal, built into the device, or external. The design and placement of antennas impact the coverage area and signal strength. Some access points have adjustable antennas that can be positioned to optimize coverage. The network interface connects the access point to the wired network. Typically, this is an Ethernet port that links the AP to a router, switch, or network hub. The interface ensures that data can flow between the wired and wireless segments of the network, enabling seamless connectivity for wireless devices. The examples of access points. Standalone access points are the standalone APs are independent devices that provide wireless connectivity without needing a central controller. They are easy to set up and manage, making them ideal for small to medium-sized networks, such as homes or small businesses. These APs are typically configured through a web interface or mobile app, allowing users to manage settings like SSID or network name, security protocols, and channel selection. The controller-based APs are managed by a central controller that oversees multiple access points within a network. This centralized management allows for more efficient control, monitoring, and configuration of the wireless network. Large enterprises and organizations use controller-based APs to ensure consistent performance, security, and coverage across large or complex environments. The controller can optimize network settings, distribute traffic loads, and implement security policies across all APs. The mesh APs are part of a mesh network system, where multiple access points work together to provide seamless wireless coverage over a larger area. Each AP in a mesh network communicates with the others, dynamically routing data to ensure optimal performance and reliability. The mesh networks are ideal for large areas or environments with obstacles that can interfere with signal coverage, such as multi-story buildings, campuses, or outdoor spaces. They provide a robust and flexible solution for extending wireless coverage and ensuring consistent connectivity. In summary, the access points are essential networking devices that enable wireless devices to connect to a wired network using Wi-Fi. By extending wireless coverage and bridging wired and wireless segments, APs play a critical role in modern network infrastructures. Understanding the components and functionality of access points helps explain how they perform their tasks effectively. The radio transceiver, antennas, and network interface work together to provide reliable wireless connectivity and seamless integration with the wired network. Different types of access points, including standalone access points, controller-based access points, and mesh access points, cater to various networking needs. By enabling reliable and efficient wireless connectivity, access points support the diverse and dynamic nature of modern digital communication, ensuring that users can stay connected wherever they are. Next, we will look into the firewall. A firewall is a security device that monitors and controls incoming and outgoing network traffic based on predetermined security rules. It establishes a barrier between a trusted internal network and untrusted external networks, such as the Internet, to protect the network from unauthorized access, attacks, and other security threats. Firewalls can be implemented as hardware, software, or a combination of both. The firewalls play a critical role in network security by enforcing security policies and protecting networks from various threats. Here's a closer look at how firewalls perform their functions. The firewalls continuously monitor incoming and outgoing network traffic, analyzing data packets based on predefined security rules. These rules specify which traffic is allowed to pass and which is blocked, ensuring that only legitimate and safe traffic enters or leaves the network. By controlling traffic flow, firewalls prevent unauthorized access to the network, mitigate the risk of cyber attacks, and protect sensitive data. The firewalls establish a barrier between trusted internal networks and untrusted external networks. This barrier is essential for preventing external threats, such as hackers and malware, from infiltrating the internal network. The firewall acts as a gatekeeper, scrutinizing all traffic that attempts to cross the boundary between the internal and external networks. Let us now understand the components of firewalls, which helps explain how they perform their functions effectively. The packet filter component inspects individual packets of data as they enter or leave the network. It evaluates packets based on criteria such as source and destination IP addresses, port numbers, and protocols. The packets that meet the predefined rules are allowed to pass, while those that do not are blocked. Packet filtering provides a basic level of security by preventing unauthorized traffic from accessing the network. The stateful inspection, also known as dynamic packet filtering, goes beyond simple packet filtering by monitoring the state of active connections. It keeps track of the state and context of each connection, allowing it to make more informed decisions about which packets to allow or block. By understanding the state of a connection, stateful inspection firewall can detect and prevent certain types of attacks that may not be apparent through simple packet inspection. The proxy server component acts as an intermediary between users and external resources, such as websites or online services. When a user makes a request, the proxy server forwards the request on behalf of the user, retrieves the response, and sends it back to the user. Proxy servers provide additional security by hiding the internal network's IP addresses, filtering content, and caching frequently accessed data to improve performance. Let us now look into few of the examples of firewalls. Hardware firewalls. The hardware firewalls are dedicated physical devices designed to provide network security. They are placed at the network's perimeter, between the internal network and the external network, such as the Internet. These firewalls offer robust protection and are commonly used in enterprise environments where high performance and reliability are critical. Examples include Cisco ASA, Fortinet FortiGate, and Palo Alto Networks firewalls. The software firewalls. Software firewalls are applications installed on individual devices or servers. They control network traffic to and from those devices, providing a customizable layer of security. The software firewalls are suitable for personal computers, servers, and other endpoints, offering flexibility and ease of configuration. Examples include Windows Defender Firewall, Norton Firewall, and Zone Alarm. The next-generation firewalls, NGFW. The next-generation firewalls combine traditional firewall capabilities with advanced security features. They provide comprehensive protection by integrating multiple layers of defense into a single device or software solution. The NGFWs offer features such as intrusion prevention, deep packet inspection, application awareness, and advanced threat protection. Examples include Palo Alto Networks, Check Point, and Cisco Firepower. In summary, the firewalls are essential security devices that monitor and control network traffic based on predetermined security rules. By establishing a barrier between trusted internal networks and untrusted external networks, firewalls protect networks from unauthorized access, attacks, and other security threats. Understanding the components and functionality of firewalls helps explain how they perform their tasks effectively. The packet filter, stateful inspection, and proxy server components work together to provide comprehensive security, ensuring that only legitimate and safe traffic can enter or leave the network. Different types of firewalls, including hardware firewalls, software firewalls, and next-generation firewalls, cater to various security needs. By enforcing security policies and protecting networks from various threats, firewalls play a critical role in maintaining the integrity and security of modern digital communication. Let us now discuss about the gateway device. A gateway acts as a node that routes traffic from a workstation to the outside network. It serves as an entry and exit point in a network, enabling communication between different networks that use different protocols. Gateways perform protocol conversion, data translation, and security functions to ensure that data can travel between networks efficiently and securely. The gateways are critical components in network communication, facilitating the flow of data between different networks and ensuring compatibility between different protocols. Here's a closer look at how gateways perform their functions. Routing traffic. The gateways route traffic from a local network to an external network, acting as a bridge between the two. They analyze data packets and determine the best path for the data to travel to reach its destination. This routing function is essential for enabling communication between devices on different networks, whether within a local network, between local networks, or across the Internet. Protocol conversion. Gateways perform protocol conversion to enable communication between devices that use different communication protocols. This involves translating data from one protocol format to another, ensuring that data can be understood and processed by the receiving network. Protocol conversion is crucial for interoperability between different network architectures and technologies, allowing seamless data exchange. Security and filtering. Gateways incorporate security functions to protect the network from unauthorized access and threats. They use firewalls to monitor and control incoming and outgoing traffic based on security rules. In addition to firewalls, gateways may include other security features such as intrusion detection systems, IDS, and intrusion prevention systems, IPS, to enhance network protection. Understanding the components of gateways helps explain how they perform their functions effectively. Protocol translators. The protocol translators are essential for converting data between different communication protocols. This component ensures that data from one network can be correctly interpreted and processed by another network with a different protocol. Protocol translation enables interoperability and seamless communication between diverse network systems. Routers. The routers within gateways direct data packets between networks, determining the best path for data to travel. They use routing tables and algorithms to make routing decisions, ensuring efficient and reliable data transmission. Routers also perform network address translation, which allows multiple devices on a local network to share a single public IP address for Internet access. The firewalls are integrated into gateways to provide security functions. They monitor network traffic and enforce security policies by allowing or blocking data packets based on predefined rules. Firewalls protect the network from external threats, such as unauthorized access, malware, and cyber attacks, ensuring the integrity and security of data transmission. The examples of gateways are VoIP gateways. The VoIP gateways convert voice traffic from the traditional public switched telephone network, PSTN, to IP-based networks. This conversion allows for voice over IP communication, enabling voice calls to be transmitted over the Internet. The VoIP gateways provide features such as call routing, codec translation, and signal conversion, facilitating seamless communication between traditional and IP-based telephony systems. The email gateways. They manage the transmission of email messages between different email servers and networks. They provide protocol translation, ensuring that email messages can be exchanged between systems using different email protocols. The email gateways also offer security features such as spam filtering, virus scanning, and data loss prevention, DLP, protecting the email system from threats and ensuring the integrity of email communication. IoT gateways. The IoT gateways connect Internet of Things, IoT, devices to the Internet or other networks. They provide protocol translation, data processing, and security functions, enabling IoT devices to communicate and exchange data. The IoT gateways handle various IoT communication protocols, such as MQTT, CoAP, and HTTP, ensuring interoperability between IoT devices and systems. They also process data locally before sending it to the cloud, reducing latency and improving efficiency. In summary, gateways are essential networking devices that facilitate communication between different networks and ensure compatibility between various protocols. By routing traffic, performing protocol conversion, and providing security functions, gateways enable seamless data exchange and protect networks from threats. Understanding the components and functionality of gateways helps explain how they perform their tasks effectively. Protocol translators ensure interoperability, routers direct data packets, and firewalls provide security, making gateways critical for network communication. Different types of gateways, including VoIP gateways, email gateways, and IoT gateways, cater to various networking needs. VoIP gateways enable voice communication over IP networks, email gateways manage email transmission and security, and IoT gateways connect and secure IoT devices. By enabling reliable and efficient communication between diverse network systems, gateways play a crucial role in the functioning of modern digital networks, supporting the diverse and dynamic nature of network devices and applications. To summarize, in this lecture, we've introduced you to the fundamentals of networking and the OSI model. Networking enables seamless communication and resource sharing between devices through various network types such as LAN, WAN, MAN, PAN, and VPN. Each network type has specific characteristics and applications, from small, localized networks to large global systems. We also discussed the OSI model, the 7-layer framework that standardizes network functions, making it easier to design, implement, and troubleshoot networks. The first few layers, such as the physical layer and data link layer, deal with transmitting raw data, while higher layers like the transport layer and application layer manage data flow and user interactions. In the next lecture, we will begin to explore the TCP/IP model and the IP protocol, the two essential components of modern networking that ensure reliable data transmission and efficient routing across the Internet and local networks. See you in the next lecture.